Welcome to the third video in our pre-matriculation lesson. In this lesson we're going to cover a little bit more detail about how the heart works on a cellular level, starting with the action potential. So first, let's take a little bit of a macroscopic view again of how the heart works. So we have the cardiac output, which I mentioned in the first video. That's the amount of blood leaving the ventricle per minute, okay? And that is equal to the heart rate, which is the number of times that this heart contracts per minute, times the stroke volume, which is the amount of blood ejected every time you contract, okay? So a typical cardiac output, about 5 liters per minute. So this is a result of the fact that a typical heart rate is about 70 per minute, although it varies quite a lot depending upon the conditions. And this is controlled by the autonomic nervous system, which we're going to cover in the last video of this lesson. The stroke volume, the amount ejected per beat, is about 70 to 75 milliliters. It varies a little bit, not as much as the heart rate. 70, a typical heart rate, 72, a typical stroke volume. If you multiply those two together, you get 5,000 milliliters per minute, or 5 liters per minute cardiac output, okay? The way that the heart contracts is through the action on the cellular level in terms of the cardiac myocytes. So every beat, you eject blood because the muscle cells are contracting and decreasing the volume of the ventricular chambers. So when we look at myocardial cells, there are actually many individual cells, okay, here. They're tubular, they're about 100 microns in length by about 20 or so in diameter, and these are all connected together in what we call a syncytium. So each individual cell is bordered by what we call intercalated discs, and the intercalated discs are where one cell connects to the next cell, connects to the next cell. When we say that the cardiac muscle acts as a syncytium, that means in many ways, especially electrically, these cells all work together as if they're one cell, okay? And the reason that happens is because they're all connected at the intercalated discs. And you can see sort of what this looks like a little bit in a schematic here. These intercalated discs have two connections. One is desmosomes, which are sort of like anchor points, which hold, these are just physical anchors, which hold the membranes of these two adjacent cells together. And then also within the intercalated discs, more importantly for our purposes, are the gap junctions. And these are channels that connect one cell to another. And they're very large cells, which allow ions to go through very easily. Another way of saying that is that they're electrical connections. So what happens is that if I have an action potential, which is a change in membrane potential, which is initiated somewhere up here, and if there's an action potential in this cell, it will result in an action potential being generated in this cell because these two cells are connected electrically as if they're one cell. So an action potential here will propagate and cause an action potential to fire here as if these two cells were one cell. And the reason is because of the existence of these gap junctions, which connect the two cells together. So this is a typical ventricular action potential, okay? The first thing you'll notice is that this is labeled membrane potential here on the y-axis. This is voltage, millivolts, okay? And this is time on the x-axis. Time goes from here to here, that way. This is a transmembrane potential measurement. And what that means is that your membrane voltage is the voltage inside your cell, the amount of charge inside your cell relative to the charge outside the cell. So if the inside of the cell has a lot of positive charge, more than the outside of the cell, we say that the voltage is positive because the inside of the cell is positive with positive charge relative to the outside of the cell. In this case, the first thing you'll notice is the resting potential, which is where we start before this action potential is fired. It's about minus 90 millivolts. That means that the inside of the cell is negative relative to the outside of the cell. The outside has more positive charge, the inside has more negative charge, okay? It is such that the membrane voltage, we put a number on how much imbalance there is between the two. The membrane voltage is such that it's minus 90, which is pretty low, okay? When an action potential fires, the voltage becomes less negative and eventually becomes positive. And it peaks out at about plus 20 millivolts or so. What that means is that the inside of the cell is accumulating positive charge. And at this point, we have more positive charge inside than outside, so we have a positive membrane voltage. The reason why this increase happens is because sodium channels open and sodium flows into the cell. Sodium is a positively charged ion. Positive charge accumulates inside the cell, the voltage goes up, okay? Don't worry about the details of how that happens at the moment. Just know that that's what this means. The inside is becoming positive relative to the outside, okay? We then have what's called a plateau phase. This is largely due to the influx of calcium, which I'll explain in a second. And then the membrane voltage returns back toward rest, and we're back where we started, and the membrane is ready to fire another action potential, okay? So this is the length of our action potential here, about 250 to 300 milliseconds. You'll find that that's much larger than the typical action potential in a nerve or a skeletal muscle. And there's time enough for that trouble for another day, okay? Note that these action potentials propagate. So if an action potential fires in cell 1, it propagates to the intercalated disc, and because there are gap junctions in that intercalated disc, that action potential propagates to the next cell, and the action potential fires in the next cell. So action potentials will fire, and they'll propagate from cell to cell to cell throughout the heart, okay? When the voltage goes up here, and when the inside of the cell becomes positive, it causes calcium channels in the membrane of the cardiac cell to open. And calcium flows into the cell. Calcium concentration is high on the outside of the cell, low on the inside of the cell. Calcium moves from high concentration to low concentration through the open channel, okay? And calcium accumulates in the cytosol. Calcium is also released from an intracellular organelle called the sarcoplasmic reticulum. There's high calcium in the sarcoplasmic reticulum. There's a channel in the SR membrane that opens up. Calcium moves from high concentration in the SR to low concentration in the cytosol. The cytosolic calcium goes up, and that causes cardiac muscle to contract, okay? So let's take a little bit of a closer look at these action potentials. Here's our ventricular action potential here. Below, we have the action potential in the SA node. The SA node, the sinoatrial node, is the pacemaker for the heart. And you'll notice that these two action potentials look a lot different. The first thing to notice is that I have a resting potential of about minus 90, and it's pretty steady here until the action potential fires. Unlike that situation, the membrane potential between action potentials in the SA node is rising. And what happens is it goes up and up and up until it hits a certain point called the threshold potential, and then you fire an action potential, okay? So unlike the ventricular myocyte, which sits at rest and doesn't change, this myocyte, the voltage is gradually changing in between action potentials until the action potential fires. And as you'll find out, the faster this voltage rises in between action potentials, the sooner you can fire an action potential here. So if you want to increase your heart rate, you want to increase the frequency at which action potentials fire, what you want to do is you want to cause this membrane voltage to rise faster so that you'll hit this threshold potential and fire an action potential sooner. So the sooner you fire the next action potential, the higher the heart rate happens. So this is the pacemaker of the heart because it spontaneously fires action potential. An action potential in the ventricle, your ventricular cell fires an action potential when the cell next to it fires one, and it propagates to you, and then an action potential fires in you, and then it propagates across your intercalated disc to the next cell. So this is initiated cell to cell. This fires spontaneously. And it fires spontaneously because this potential in between action potentials rises, and the faster it rises, the quicker the quicker you fire an action potential and the faster your heart rate. Okay? So I mentioned that the calcium outside the cell is higher than the inside the cell. You can see that here. We have a calcium concentration in the cell about 50 nanomolar. Nanomolar is 10 to the minus 9th. Outside the cell, it's 2 to 6 millimolar. That's 10 to the minus 3. So you're talking about a difference of 5 orders of magnitude here between the calcium outside the cell and the calcium inside. So that's a big gradient. And when calcium channels open, they flow down this gradient. Okay? And you'll notice the same thing. Sodium is higher outside than inside, and potassium is higher inside than outside. So you may wonder, how are these gradients maintained? Well, in the case of sodium and potassium, they're maintained through the action of the sodium-potassium ATPase, or the sodium-potassium pump. This pump uses the energy stored in ATP to pump sodium from low concentration in the cell to high concentration outside the cell. So this pump maintains that sodium gradient. It keeps sodium high outside and low inside. Conversely, it pumps potassium from low concentration outside to high concentration inside. It uses energy to pump the potassium uphill from low to high. So it maintains a high potassium on the inside of the cell and a low potassium on the outside of the cell. And it does that by hydrolyzing ATP and using the energy in ATP to generate these gradients. The calcium gradients are generated when we're talking about the inside of the cell versus the outside of the cell. We're talking about sodium-calcium exchange. In this case, you're transporting sodium from inside the cell at low concentration to outside the cell at high concentration. And the way it does that is by allowing sodium to flow down its gradient from high to low. And as sodium flows from high concentration to low concentration, calcium is pumped from low concentration to high concentration. We call that secondary active transport. It's secondary because it's actually using ATP to do it, but indirectly. The sodium-potassium ATPase maintains the sodium gradient by using ATP, and then the sodium-calcium exchanger uses that gradient and allows sodium to flow down that gradient in order to pump calcium up its gradient. So the sodium-calcium exchanger keeps calcium high on the outside and low on the inside. We have calcium pumps as well in this cell. The big one is in the sarcoplasmic reticulum membrane. It pumps calcium from low concentration in the cytosol to high concentration in the sarcoplasmic reticulum. We'll talk about that in a minute. Okay? So, how do action potentials propagate through the heart? They start at the SA node, right here, and they propagate from there through the atrium, okay? You'll notice on this side we have different action potentials. They're actually lined up in time. So the SA node is first, the ventricle is last. This is the atrial muscle depolarizing. As that happens, your atrial cardiac cells contract. The process of contraction is initiated by the action potential and the influx of calcium that goes with that. From there, the action potential goes to the atrioventricular node, which is a little piece of tissue between the atria and the ventricles. That's here. From there, it goes into the ventricle. And what it does is it travels down the bundle of His, which has Purkinje fibers in it. And these conduct action potentials very rapidly down the septum of the heart and out along the interior of the walls of the heart. Okay? Here, down here to here, and down here to here. And then from there, the action potential goes through the ventricular muscle from inside to outside, and that's causing your muscle to contract in a nice, even manner. Both ventricles contract at the same time as the action potential propagates through the tissue, and calcium initiates the process of contraction. So that's how this operates. Okay? All right. So that's the end of this video.